Section 8.3 is the integral and comparison test. So this is just expanding on our means of testing convergence of infinite series. This will go beyond what we saw in the last one with the geometric series and the divergence test. So the first thing we'll use is the integral test. It's essentially one singular implementation of it to establish test for the p-series. So the integral test is really similar to what we saw before when we wanted to find the limits of a sequence. So we rewrite a sub n as a function f of n. N is taking integer values from 1 to infinity. We're considering its series, n equals 1 to infinity of a sub n. So we have a characterization that this series is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. So here's the trick. We just went from a sub n equals f of n, matching that to f of x, just as we did for limits of sequences in 8.1. So again, the notion is to switch to a continuous variable. That's the only thing that's appropriate for an integral like this. So it's kind of important to do a formal switch to x instead of doing things in terms of n, even though it's not technically wrong to do it in terms of n. Anyway, the convergence is as follows. From 1 to infinity of the function f of x dx, if this integral converges, then we know that our series n equals 1 to infinity of a sub n converges as well. So essentially it follows suit. On the other hand, if this integral diverges, then we know that our series also diverges. So it's a really handy tool. Of course, the crux of the matter is whether or not the integral from 1 to infinity of f of x dx is actually convergent. And we'll notice there are a lot of sequences or series that have things like factorials and discrete operations in them that don't lend themselves to a function of a continuous variable. Okay, so down below is a picture of more or less what the integral test is doing. So if we look on the x-axis, we're numbered along the integers 1, 2, 3, so on. Each of these is our index. The height, and we're forming rectangles. The height of each of those rectangles is actually the value of the sequence at that index. So A1 has a height of A1, it's at index 1. The width of each of these rectangles, we'll notice, is actually 1 from each of these integer steps. So the area of each of those rectangles is just the height of the rectangle. It's the height times the width of 1. So we're able to establish that all of these areas for each of these rectangles that we're forming are actually the sums that we're seeing in our series. So you can see that at the points where f of n matches a sub n, or f of x matches a sub n, the corners of the rectangles here, that we can link the behavior of the rectangles to the curve. So if the curve is convergent, all these rectangles fit underneath it, well, then we know that the area under the curve is convergent or finite, and all the rectangles fit underneath it. We know that we've got a finite sum of rectangular areas, so we have a finite series or convergent series. On the other hand, a different picture, not drawn here, but one in the textbook would show you that we'd have overlapping corners coming this way. Would be another way to set this up by an index shift. I won't go through the details here, but the textbook can show you that. And if that curve is divergent, if we have an infinite amount of area underneath that f of x function, then we've got a divergent series as well, because the area is a little more than the curve. And of course, if the curve has infinite area under it and we're overlapping it and then some, then we're going to have more area in the series. So that's about all as theoretical as this section is going to get. From here, we're going to use the integral test once, and then we're going to establish convergence and divergence for the p-series. And that'll be our main tool, and it'll lead us into limit comparison and the comparison test. So our first example, we're asked to use the integral test to determine the values for which the p-series converges or diverges, where p is a given real number. Our series is n equals 1 to infinity. The term is 1 over n to the p. It's really important now, students new to this, sequences and series, which is probably mostly everybody, to note that this is to a power of p. P is fixed, okay? N is the denominator, it's the base of the exponent in this. So don't get this confused with the geometric series. This is critical. The geometric series would look something like this: 1 over r to the n. R is a fixed ratio. N is the exponent versus being the base of the exponent. Okay, so these are distinctly different. A geometric series is an exponential function. A p-series is a rational function. So keep that in mind. N is the variable in both cases, but it's the base of the exponent for this rational function, polynomial over polynomial, versus the exponential case for the geometric series. So at any rate, this is one of the easiest series to assess convergence for, because we're just going to use the integral test right away. We have our series term as 1 over n to the p. Match that or rewrite it as a function of a continuous variable. F of x equals 1 over x to the p. We've been given that x is a real number. We might say that x is not, or sorry, p is a real number. We might declare that p is not 0. That would be a trivial case or a divergent case, but we'll probably see that in the analysis that follows. So the integral test, once we've got our continuous function f of x, we evaluate the integral from 1 to infinity of 1 over x to the p. This is an improper integral since we're running to an infinite limit. So we have the limit as capital R approaches infinity. So now we have a finite definite integral with a limit on the outside. 1 over x to the p is rewritten as x to the negative p through exponential notation. This is just a power rule antiderivative. The result of that is x to the negative p plus 1 divided by that new exponent. There's nothing new here. And evaluate from 1 to r. Now we've moved some minus signs around in this and cleaned up the expression. 1 over 1 minus p is coming from this denominator being factored away from the function of x. And we evaluate now from 1 to r of x to the 1 minus p. We have r to the 1 minus p minus 1 to the 1 minus p. Of course, that term is going to be 1. And r to the 1 minus p as r goes to infinity. Well, now we have two possible cases. If 1 minus p is less than 0, in other words, if that's negative, then we're actually seeing that this term right here is 1 over r to the 1 minus p, or negative 1 minus p. At any rate, this is shrinking as r goes to infinity. We're taking it to large, we're sending it to a negative power, and we're growing that as we go. It's in the denominator, so it's going to shrink as r goes to infinity. So that's our convergent case. If 1 minus p is greater than or equal to 0, we've already seen that if 1 minus p was equal to 0, that's p equals 1, and that was a problem. Oh, sorry, p equals 0. That's a problematic case. So again, our convergence is here at p is greater than 1. Okay. Again, the student can test to make sure. You might use an example. Let r be equal to 2, possibly, and then check what if p was to be equal to. So 1 minus p, it needs to be less than if it was if p was 2, maybe you might try p equals 2, and that would be 1 minus 2 is less than 0, and you could see that this thing would actually be a convergent limit as r goes to infinity. Again, not necessary, but just an example since we're sort of in a more abstract notation right now. So that's our convergence case. Otherwise, this thing diverges because r, we're taking some real number r to a positive exponential power, and we're letting r run off to infinity. So of course, it's going to grow. So here are our cases below for the p series. This integral, we'll see it a lot. We're going to use it for comparisons. It converges if p is strictly greater than 1. It diverges if p is equal to 1 or less than 1. You might also note this. If p is equal to 1, that's 1 over n. And we recall that that's the harmonic series from the last section. We proved more directly that the harmonic series diverges, or we made a good argument for it, but now we've got a very official proof of that through the integral test. So that's our first example. It's almost the only thing we'll use the integral test for. There might be a couple exercises that might test your ability to use it, but otherwise, the integral test is a block that sets up the p series, and then the p series is our fundamental comparison series for most of what we do in the next two sections. So let's look at one evaluation with the p series here. So here's our theorem in print for what we just established in the previous problem. And we're given the series S, it's n equals 1 to infinity of 1 over the square root of n. And of course, the game is to convert square root of n to the 1/2. And then note what p is. P is equal to 1/2. 1/2 is less than 1. So we just conclude directly from this theorem that it's going to be a divergent p series. So this is just a matter of classification at this point. It's a nice quick example to see. So estimates of sums, there are two versions of this in this section. I won't go too deeply into the details of this because the way that we'll estimate sums, what this page essentially amounts to is just cranking out series terms, adding them together, and just cutting off when you've met your decimal precision. In other words, when the third decimal place doesn't change anymore when you add a term, you're at 3 decimal places of accuracy. So that's sufficient for what this is telling us here. And it's probably sufficient for anything we're going to do in this class as well. But note that there's a good bit of analysis that can be put into this, and the textbook does that. Perhaps in a live meeting, we could go over some more of this at some point. So just to see that estimate of sum scenario, let's have a look at this example. They say find the sum of the series correct to 3 decimal places. We've got 1 over n to the 5th, n equals 1 to infinity. And we just start writing terms out, right? It's exactly as I explained it previously. And we add terms until our third decimal place, 3 decimal places, until that third decimal place doesn't change. And it looks like at n equals 5, going out to the 5th series term, we can see that the decimal place is not going to change after this. So you could check by adding another one, right? Or we could see down below that we said that 1 over 5 to the 5th is actually this decimal with 3 leading zeros in the decimal place. So it's not going to change the front 3 decimal places or the first 3 decimal places after the decimal point. So we've met our degree of accuracy. Checking a term, you could just crank it out until the third decimal place doesn't change anymore. So there might be a little bit of a shift. You might want to go several terms after just to be sure, but that's just the nature of approximation. More iterations will get you closer to the answer. So that's it for sum estimation. In the next video for 8.3, we'll follow up and do the comparison theorem and the limit comparison theorem, which are two of the most important integral or convergence tests that we'll do in all of chapter 8.